Okay, so this is the last section in chapter 18, and I'll be doing the review next time. So this is using the conservation of energy in order to solve problems, and you can use this principle of conservation of energy when there are essentially no dissipative forces. There are only there's kinetic energy, there is potential energy like spring energy and gravitation energy. Okay, so this is so a few things before we start solving problems. Okay, the principle of conservation of energy is that the kinetic energy plus potential energy at one instant of time equals the total energy, the kinetic energy plus potential energy at another instant of time. Okay. So when we do rigid bodies, the kinetic energy is going to be sum of two parts. There's going to be energy due to translational motion, half mv squared, and there's going to be energy due to rotational motion. Okay, that comes due to inertia. The potential energy is there are two things we'll be concerned about in this chapter. There is the gravitational potential energy. Okay, and that is denoted by Vg, and it equals the weight, which is mg times the distance moved in the y direction. Okay. So when solving problems related to, or when you want to find the potential energy, you want to start with a datum, a line which has energy equal to 0 or potential energy equal to 0, and then the energy of the mass depends on where you are from the datum. So if you move upwards by a distance of y, or that capital G for the center of mass, then the potential energy is mg times yg, and the sign for that is positive, and that's because when you move an object upwards, it has the potential to do work on the system. Okay. Note that that is different from our definition of work done. When you move a mass upwards, you're moving it, the y is plus, but mg is downwards, so the work done is going to be negative. However, the potential has the sign exactly opposite to that convention. You don't get confused. When you move the mass down, like so, yg is negative, and the potential is also negative. Okay. Again, this is the opposite sign to that of work done. The other potential is the elastic potential energy, and this is the energy stored in a spring. Okay, the most common spring is the one in which the force is proportional to the displacement s, in which case the energy is going to be half k s squared. It's not going to be true if the spring was non-linear, like there was one problem sometime back where the force was kx squared, in which case the energy will not be half k s squared. You'll have to integrate the energy, or you will do force times displacement and integrate that to get the potential. So this is only true for a linear spring. Okay, so a caricature would be the spring is unstretched, That is, the force in the spring is 0 when it is unstretched. It's also called the zero length of the spring. If you stretch the spring by distance s, then the potential energy is half ks square, the positive sign. If you compress the spring by the same distance, okay, minus s, the potential is still half ks squared. So the potential is always positive, irrespective if the spring is stretched or not. And that's because when you either way, you compress the spring or you stretch the spring has energy which can use to do work. Just like our displacement analogy, right? When you move the mass up, it has ability to work. When you move it down, it does not have an ability to do work. It's negative work. But in this case, no matter what you do to the spring, it always has that energy stored which it can use to do work. So the energy is always positive, irrespective of you compress it or not. Okay, is this clear? And the final thing I wanted to say was you're not restricted. Now, this conservation of energy only holds when there's no dissipation, right? There is no friction, there's no drag force. If, however, you had drag forces and you wanted to use the principle of conservation of energy, then you got to account for the fact that drag force or that friction force is going to dissipate energy. So when there is dissipation, so T1 plus V1 equals T2 plus V2 in the normal case, but if there is dissipation, then you have to account for the work done by dissipation. Work done by dissipation. Okay? So once you find the work done by dissipation, you can use the conservation of energy and solve for whatever you're interested in, like the energy at instant T2, so on. Okay. Any questions? Okay, let's start solving problems. This is question 1 for today. Okay, let's read it. A slender 6 kg bar AB, so 6 kg bar AB is horizontal at rest and the spring is unstretched. So this is the free length of the spring. That is, the force in the spring is 0 when it's unstretched. Find the stiffness K of the spring so that the motion of the bar is momentarily stopped when it has rotated clockwise 90 degrees. So clockwise is this way. So when it's released, the bar sags down and it comes to stop at this point when it's vertical. Okay, you got to find the spring constant K so that when released, this bar will come to rest in its vertical position. Okay, so this is at rest. This position is also at rest. Okay. So the reason why you would choose principle of conservation of energy is because there are no dissipative forces. The only forces are gravitational and potential due to the spring, and what else? There's kinetic energy, but that is going to be 0 at the 2 points. Okay, so it looks like conservation of energy is the right thing to do. Conservation of energy. Okay, so you need to choose instances of time at which you're going to apply the conservation of energy. T1 plus V1 equals T2 plus V2, where 1 is going to be the instant when the bar is horizontal, and 2 is going to be the instant when the bar is vertical. So find the energies at those two instances, equate the two to find the spring constant K. Okay. So the the kinetic energy at 1 is 0, it's at rest. Let's do the easy ones first. The total energy at 2 is 0 because it's also at rest at instant 2. You want to find the potential energy at 1. Now potential energy consists of two things. One is elastic due to the spring and due to gravity. Okay, there are two potentials here. Now for both cases you got to fix a datum in order to find the energy. So let's just assume that the datum is basically the line AB in its horizontal position. So I'm going to redraw this. This is my datum. Okay. For no good reason, you could also use the datum to be this way, this, whatever you want, whatever makes your life easy. Normally, it's much easier if you choose the datum to be one of those equilibrium positions, or it passes through like in this case, the mass is here. So you might want to put the datum through this so that the potential due to that is 0. Try to sort of cancel off as many potentials as you can, just like you would cancel off any forces by choosing the moment point to be at the point where maximum forces passes. Remember, this was done in equation of moment, where you chose the points that most forces would pass to that, similar to that. So in this case, I'm going to arbitrarily choose the datum to be the horizontal position. Okay, so then so there is two things. There is the elastic potential and there is the gravitational potential. Okay, what's the elastic potential? It's 0 because the spring is unstretched. The elastic energy in a spring is half k s squared, but the displacement is 0, so the potential is 0. What's the potential due to gravity? It's also 0 because when you have the body on the datum, so this is where the center of mass is, and that passes through the datum, so that's also 0. Okay, so V1 is 0. Let's find V2. Okay, V2 is when bar is this way. This is where mg is going to be. Right? This is not a free body diagram, by the way. Okay, so again we have two parts. There is potential energy due to spring, potential energy due to gravity. Okay. Okay, let's do the potential energy due to the spring constant. So the potential energy is half k delta s square, or it's the extension in the spring. We're going to find that. Once we find that, we'll sub it there. What's the potential energy due to gravity? Okay, it's clearly mg times the distance moved from the datum. So this distance is 1 meter, right? It moves the center of mass moves the distance of 1 meter. That's 1. But what's the sign? Is it positive or negative? It's negative because remember, when you move something down, you do negative work, and so that's negative. Okay, so mass is known, gravity is known, k is an unknown. This is V2. We have to just find what delta S is. Delta S is the extension in the spring. Okay, so delta S. Delta S is the spring length. So this is the point C, this is point A, this is point B. So initially the spring is this way, and then the spring, since it's attached at point B, this is how it's going to be. It's going to be stretched. So this distance is 1.5. Okay. So it's the new delta S is the new length of the spring in this position. We call this CB prime. Okay, it's going to be CB prime minus the original length of the spring, which is CB. Okay, CB is 1.5. We just have to find CB prime. Okay, so let's do some trigonometry. Okay, do we know this? We know this is 2 meters, right? Because that's going to be the length of the bar, 2 meters. Okay. What else do we know? How can we find CB prime? What's that? Say that again. I didn't get that. Pythagoras theorem. Okay, so if you want to use Pythagoras theorem, we need to find, we know what C, let me call this point O. We know what CO is. We have to find P prime O, right? In order to use the Pythagoras. So what's this? That's 2 meters. That's because this length is 2. So CB prime is square root of, well, it's 2 plus 1.5, it's 3.5 square minus 2 square, sorry, plus 2 square. That comes out to be, anybody can do the math on that? I don't have the answer here. 4.03. Okay. And CB is 1.5. So we are set to go. So this is the total, the conservation of energy. T1 is 0, V1 is 0, T2 is 0, V2 is this thing here. It's half K 4.03 minus 1.5 square plus mass is 6 kg, so 6 kilograms times 9.81 times 1. I think I'm missing a sign, so this is negative. Okay, so everything except K is known in this equation, so we can solve for K. It's 18.53 Newton per meter. Okay, is that clear? Any questions on this? So when you have a spring problem, I would highly recommend that you draw a figure like this, the way I've drawn it, because it's very easy to get confused in finding the correct length of the spring, and you need to know the length of the spring in order to find the potential energy. If you have to draw multiple figures, please draw them. Don't be just draw it. Don't worry about drawing multiple figures. But clearly label your figures. If you want us to grade your FPD, write FPD there. There's no FPD. I've not drawn an FPD in this figure. That's why I did not write FPD. But it's always a good idea to draw an FPD if you think you need it. Okay, a system consists of a 60-pound and 20-pound blocks A and B, respectively, and a 5 lb pulleys C and D. This can be treated as discs, so these are discs. Find the speed of block A after block B has risen 5 feet. So block B has risen 5 feet. Okay, obviously A is going to move down from rest. Assume that the cord does not slip on the pulleys and neglect mass of the cord. So when this thing is released, because A is heavier and because of the kinematics, A tends to go down, B goes up. You're going to find the velocity of both A and B when that happens, when B has moved 5 feet. Okay. So this is, well, is this a problem of conservation of energy? Is there friction? There's no friction. There's only gravitational potential. There is potential due to, well, there is kinetic energy change, right? So it is a problem of conservation of energy. Now, when you write the conservation of energy, well, we can write the conservation of energy, and then we'll realize that we have to do some other arithmetic. So I'm going to start with the conservation of energy. Okay. Again, you got to choose two instances of time, and clearly those instances are going to be the initial position, which is shown so, and then it will be the position after B has moved up and A has moved down. So T1 plus V1 is T2 plus V2. Okay. So what will happen is when we write the energy, we'll have half mVA square, half mVB square. We'll also have mg times distance moved by A, mg times distance moved by B, and we will have to resolve the fact that we only know the distance moved by B, but we don't know what the distance moved by A is, right? And so what we need to do is we need to find what is the relation between motion of A and B. So we got to do some kinematics. So let me do the kinematics first, and then try to write the equations. But this is one way to think about it. Try to ask yourself, what do you need in order to solve this, and then try to write the other equation. So kinematics. Okay, kinematics is going to tell me the relation between motion of A and B. So for that, and this is going back to the first chapter we did. We need to assume an origin or a datum, assign distances. So since there is only a single cable tied around the pulleys, I would have two unknowns, XA and XB. If there were two different cables, then there will be three unknowns and so on. Okay. So given that, I can find the length of the cable which wraps around pulleys C and D as XA is, well, let me put this as XA. Okay, XA plus this length plus this length. So it's going to be plus twice XB is a constant. The length of the pulley is constant. So if we differentiate that, we can get the displacement of A plus twice displacement of B is equal to 0. Or in other words, delta XA is minus 2 delta XB. The other way we could use this expression is we could differentiate the expression with respect to time, in which case L dot will be equal to 0, and XA dot plus 2x dot B is equal to 0. And I'm going to write V is the velocity instead of x. So velocity of A is minus 2 times velocity of B. Okay, same expression, but the way you interpret it is different. This is telling about the displacement, the other one is telling about velocity. So that's known. Delta XA is minus 2 delta XB, which in this case is XB is 5. Okay, and it's going to be 5 upwards. So I'll put, well, let me put 5 here and it's minus 10. Just saying that the motion of A is going to be opposite to that of B. If 5 is positive upwards, then B is going to be downwards, negative 10. Okay, got that. Let's move on to the conservation of energy. Okay, T1 is the initial kinetic energy, and that is 0. T2 is the final kinetic energy, and that's going to be energy MAVA square plus half MB VB square plus, what else? There is energy due to the pulleys rotating. So half IC omega C square plus half I D omega D square. Okay. Now VB is what? Well, let's keep VB. Let's try to solve for VB. So we'll sub in the value of VA. VA is minus 2 VB. Okay, so we can write that expression in terms of VB. Omega C is basically the rotation of C. Okay, that is related to velocity of A by the following expression: velocity of A divided by the radius of that particular pulley, which is pulley C. This is R of C. It would give me the angular velocity, because if this point doesn't slip, then V equals omega R. Similarly, omega D is going to be VB divided by the radius of disk D, which is going to be 0.5, right? Because the velocity associated with this point is VB and not VA. But VA is minus 2 VB. Oh, I forgot half, sorry. It should be 1/2. So T2, the expression T2 is only in terms of VA. Okay, there is no, sorry, it's only in terms of VB, it's not in terms of VA. Okay, I am out of time. Just give me 2 minutes and I'll finish this. Okay, I'm just going to take 2 more minutes. Okay, V1 is the potential energy at instant 1, at this instant of time. Okay, so let's write the potential energy of the different blocks. So there's MAG times XA. Okay, is that positive or negative? It's negative because the datum is up. MBGXB, is that positive or negative? It's positive. No, the datum is here, so it's going to be negative. And then since C is on the datum, the potential energy due to C is 0, right? The only thing left is MDGXD, and that is also downwards compared to the datum. So that's V1. Okay. The last thing left in this expression is V2. Okay. So let's write that down, and I'll let you go, because then it's a matter of putting it in the expression and simplifying. So it's MAG. XA moves downwards. Okay, so the distance moved by XA is XA plus, what's the distance moved by XA? It's 10 feet downwards. Right? XA plus 10 is the distance moved by it downwards, so it's positive. Well, this is positive, but the potential is negative because it moves downward. It's XA plus 10 from the datum. Similarly, it's going to be MBG. The block B moves 5 upwards, so the net distance moved is XB minus 5, but there's a negative sign because it's again downwards compared to the datum. And then finally, MDG XD minus 5, because the point D and point B have the same distance moved, it's 5, so that's negative. So all that is left is to put V1, V2, T1, T2 in the expression for energy and solve for velocity. I'll finish this and post it later today.